Hi, my name is Han. I'm a rising senior at the University of Michigan, the Electrical Engineering and Computer Science Department. Today, I'm going to talk about my summer research project, characterizing mechanical properties of microsprings for MEMS devices. My mentor is Professor Najafi and Dr. Peterson. Microspring is a very important structure in the microelectromechanical systems. We call it MEMS. It has a wide application in the MEMS devices like microactuators and micro transducers. So it can provide both elastic force and transfer energy. So my research goal is to calculate the spring constant and the resonance frequency in x, y, z direction to understand the relationship between the spring parameters like the length, width, and thickness, and related to the frequency in order to generate the design rules. Third is to verify the results by the experiment. So I'm actually using shaker table and laser vibrometer. So let's take a look at the layout of the spring. So actually, we have fabricated two types of springs. First is called classic serpentine spring, which is used for x direction vibration. The second one is rotated serpentine spring. It can be used for the y direction vibration. So we concern about the planar behaviors. So these two springs are good choice for x and y direction. So this picture shows we have 7 different size springs for each type available. Let's take a look at the spring configuration. In order to analyze the property of the spring, we have to divide the spring into 3 parts: the initial one, the repetition part, and the finish part. Note here the P and null term, like LP and L null, denotes the horizontal sector and the vertical sectors. So this diagram summarizes all the measurements of the parameters. So you can see all the length units are measured in micrometer. As a fact, a human hair is approximately 50 micrometer in diameter. So you can imagine how small the spring is, because you can see the parameter are in like tens or hundreds of microns. So here comes the equations to calculate the spring constant. Well, these equations are only approximate equations. It's available when I start the research. But when it goes on, I found these approximate equations are not suitable for our design, because our spring do not meet the assumptions like the LP is greater than L null. So I started to use the analytic equations, which are quite lengthy and complicated. So then I just programmed in MATLAB and get the resonance frequency. Then I did the parametric test. So these 5 factors like L null, LP, width, thickness, and the number of repetitions are the main factors I really concern. So each time I change one parameter incrementally and keep the other parameter fixed. So like you see in this example, here I change LP from 10 microns to 100 microns, and here I change N from 1 to 10. So I get a set of different frequencies in X, Y, and Z direction. Then I just plot the frequency in all 3 directions in terms of the changing parameter LP. So for each test, we really concern about the crossover points, because these points are really characterizing the relationship between the spring frequency and the parameters. So there are totally 17 tests carried out for both rotated and classic type spring. Then based on our application criteria, the design rules are generated for the spring. So let's take a look at the experiment setup. The black one is a shaker table. You see it has a little aluminum block in the front of it. It's actually a dummy test platform. We are not going to use it for our real measurements. And the shaker is shaking back and forth. The white one is a laser vibrometer. It shoots a laser on the block and reflects it back, and send the signal to the controller. The controller will give an output signal. You see the little bar here. This indicates the reflected signal is pretty strong. This block diagram shows how the whole experiment works. The function generator input a signal, and it's been amplified by the power amplifier, and goes to the shaker table. Here I also put an accelerometer to the shaker because it can measure the actual movement of the shaker table. So the signal from the accelerometer and the controller both go to the oscilloscope. So you'll see this is a sample signal on the oscilloscope. The upper signal is from the accelerometer, which measures the acceleration, and the lower one is from the controller, which measures the velocity. So both of these analog voltages can be converted into the real physical meanings. So this is basically what I did in the summer. The real test platform has already been designed and is now being fabricated in the machine shop. So for the next fall, so I will go on with this project. I will just fix the microspring on the platform and measure the resonant frequency to compare with the calculated data. So this is the end of my presentation. Thank you.